shine a laser light in the night sky tonight, okay, well, maybe during the day, the light ray is going to get bent a little bit by the gravitational field of the sun. And it's going to go for a while, and then it's going to hit another star, and it's going to start bending a little more. And it's going to hit more stars, and it's going to bend a little more, and so on, and so on, and so on. And there's too much stuff in our universe that light will not be able to escape it. We live inside a black hole. Did you know that? So if you live inside a black hole, which has this, this infinity inherently in it, then you'd expect, maybe I'll get that there's a thing there, maybe you'd expect that little smaller things along that line will be just smaller divisions, smaller black holes, smaller singularity. And if they line up, they would be. So here's quasar. We know they're black holes. Here's the center of galaxies, all galaxies. We know they're black holes. From this theory, I was able to predict that we were going to find a black hole at the center of all galaxies. I got in a lot of trouble for saying that some 25 years ago. But now we found black holes at the center of all galaxies. As well, I was able to predict that the black hole at the center of the galaxy is present before the galactic formation. That is the source of the galaxy, not the result, which was the assumption that was made in the Standard Model, that the black hole in the center of galaxies was the result of all the stars colliding there and making a black hole. What I was saying is, no, the black hole is there first. That's what's producing the matter that we see as a galaxy. It's a continuous creation model instead of like one big bang, which is more of the male approach. And so then stellar objects, many star-sized objects are black holes, and then we jump from stellar objects all the way to the atomic structure. And that in physics is not expected, because currently we think that cosmological objects are dealt with classical physics, or at least Einsteinian physics, and the atomic structure is dealt with quantum physics, and the two don't agree. And most physicists will tell you they're not related. Yet, they may have not noticed, but big things are made out of small things. So obviously, they must be related. Right? Now, so here we jump all the way to the atom, and the atom falls almost perfectly on this line. Remarkable. And then all the way to the Planck's distance. You see how far the Planck's distance is compared to the atom? Imagine how teeny that is. That's the atom. You see, there's less distance between a star and an atom than between an atom and the Planck's distance. So you can imagine that's a huge scale from the universe to the Planck's distance. The odds of all these data points falling on that line are extremely low. Yet they do. If we lived in a random universe, these data points would be all over the place. So, is everything in the universe a Schwarzschild black hole? Is everything in the universe just smaller division of singularity? Singularity comes from the word singular. One. Are we only observing division of the one? Wow, this is starting to sound a lot like ancient texts and all these prophets and all these masters that have walked the earth that told us that. Maybe we should have tried applying that to physics. Yeah. But if this is true, there's a problem. This guy. Well, atoms are not thought to be black holes. So how is the atom a black hole? If you say to a physicist today, an atom is a black hole, he'll say, absolutely not. The atom is not massive enough to be a singularity. Okay, how do we deal with mass? Yes, indeed. If we look at the bottom, at the confine of physics today, the standard model has zero explanation from what mass is. We don't have a clue. We have a model that says that it's related to the Higgs mechanism, the Higgs boson, which is our current model, and, you know, is quite controversial. And in any case, that model says that the Higgs boson is a fluctuation of the vacuum itself. So, and, you know, CERN, and this is why we built the Hadron Collider, the largest accelerator ever built. $13 billion later, 17-mile long, coils so large that the first time they turned them on, they ripped off the anchors, went flying into the tunnel, and embedded themselves into the detectors. The whole thing flooded with liquid helium, and they had to evacuate. So $2 billion later, they turn it on, but it's so wide and so long of, you know, a device to maintain that some bird had placed a little crumb in the wrong place. Poof! You know? Looking for the Higgs boson, which is now seeming to not be found. In any case, what I said is, hey, are we ignoring the vacuum? Yes, we are. So if we looked at a proton, and this was in the paper, the Schwarzschild proton, that was published 2 years ago. It was published at the CASI conference in Belgium, the one I just came back from. This was the 2009 CASI conference. It received the first paper award there. I was very, very surprised because it's very controversial. Thank you. And there's been discrepancies of internet chatter about that prize. It is peer-reviewed, and it is peer-reviewed by professional physicists. And so what I did is I took the volume of this little proton, and I said, how many Planck's distances fits in it? That is, how many of these little oscillations of the vacuum are in there? Because we're not counting those. So we should count those when we're talking about the mass of the proton. We can't just ignore that. So I outputted the volume of the proton. 10 to the minus 39 is its volume. And I said, okay, in that volume, how many little Planck spheres can I stick in there? And the result is 10 to the 55, which happens to be the mass of the universe. And when that came out, I was blown away. Because I had been saying for all this time that the vacuum is the great connector, that the energy in the vacuum structure is what holds all the information, what connects every point with every other point. That means that every proton, which is the nuclei of an atom, the center of the atom, should have all the information of all other protons in the universe. And that's exactly what happened when I wrote the equation. So I was like so excited. I was actually so excited I thought I'd mention it in the Schwarzschild proton paper. I just put one sentence. I didn't want to say this is a mathematical proof that everything is one, but I put this may be evidence that all protons are entangled through the structure of the vacuum. So, but do I need 10 to the 55 grams per centimeter per proton volume for the proton to be a black hole? Absolutely not. 10 to the 55 grams is enough to make the whole universe a black hole. So that is not correct. It cannot, well, you know, it definitely makes the proton a black hole, but what I wanted to know is how much of that energy is actually expressed in the dynamic of the proton for it to be a black hole. So in order to do that, I had to use the Schwarzschild equation. Do not panic. Don't run out the doors. It's not going to hurt. Maybe just a little, but then it's okay. It's a simple equation where the radius of the system is equal, so the radius of the black hole is equal to 2 multiplied by the gravitational constant multiplied by the mass over the speed of light squared. And this is a consequence of Einstein field equation. This was the first solution to Einstein general relativity equations. It was written by Carl Schwarzschild. After Einstein published general relativity, he hadn't solved it. He thought it would take a very long time before it got solved. Carl Schwarzschild looked at it and came up with this solution, this exact solution, and sent it back to Einstein and said, your general relativity theory predicts singularity, predicts a black hole. That's the solution for a black hole. And, you know, Einstein was unhappy about that result. He thought, you know, oh my God, my equation predicts something that probably doesn't exist. At the time, the idea that black holes would exist, you know, or singularities, the word black hole was not even coined. That was John Wheeler much later. They thought it was just a mathematical point, not a real point. But they realized, I mean, eventually Einstein's general relativity got sustained by experiments and by, you know, observation. So, you know, they realized it was useful. So this equation actually is used, for instance, to figure out the orbits of the sun and the moon, right? They do the Schwarzschild solution for the sun.